Hello and welcome to part 1 of revising for the specialist exam. Now I've travelled to every state in Australia, I've read every single one of their past papers, and I'm going to start showing you some questions that wouldn't look out of place on a Queensland specialist exam. Our first stop is Victoria, way back in 2006. Multiple choice question, tech free. Give yourself 90 seconds, see how you go. And I'm going to start solving it in 3, 2, 1. There's a real trick to solving these sorts of questions, and it's to start thinking big instead of small. What I mean by that is, let's look at this first quadrant here. Every single one of the gradients in that quadrant are negative, right? Negative gradients in quadrant 1. All of these are positive. All of these gradients are positive, and all of these ones are negative. If we also look along our y-axis, that's interesting information. Every gradient along the y-axis is equal to a flat line, which is a 0 gradient. And every one of these ones here are vertical lines, which is an undefined gradient. Okay, so now that I've got all of that information, let's look at these questions here. Let's focus on, say, quadrant 1 for now, right? If x was positive and y was positive, would A result in a negative or a positive gradient? Positive squared over 2 plus a positive squared, that would be a positive gradient. But I'm looking for a negative gradient. Okay, so that doesn't work. What about this one? X squared plus y squared over 2. A positive plus a positive over 2, that's going to be positive, so that doesn't work either. All right, what about this? Negative, a positive over a positive. All right, C works, so we can hold on to that. A negative, positive over a positive. That's going to be a negative, so that works. And a positive over a positive, E doesn't work. So you can see I've already gotten rid of 2 of these options. 3 of those options. All right, what I've done here is be a little more systematic about it. Quadrant 1, only C and D work, so we're down to there. Now, we can go through quadrant 2, 3, and 4 and check that they work as well. But I think you'll find that these operate in the same way, right? Just because the x's and the y's are flipped, it's always going to be like a positive divided by a negative, or a negative divided by a positive, or a negative divided by a negative. So all of these are going to end up sort of agreeing with each other. But I can do one more just to double check. So if this was a negative, negative, and then x over here now in quadrant 2, if that was a negative divided by a positive, negative, I'm expecting a positive there, so that one works there. This one will work too. It's actually going to work for all 4 of those quadrants. And then we come down to what I would sort of say is like the tiebreaker, right? Let's look at the y-axis. Okay, along the y-axis, that's where x equals 0. Now, what happens with this one when x equals 0? Negative 0 over 2 times some y value, right? Just a y value, positive or negative. But 0 divided by any number is going to be 0. So we would expect along the y-axis, this one here to have a gradient of 0. And it does, so that's good. Whereas, if we look at this one, negative some value for y, positive or negative, divided by 2 times 0, because we're working on the y-axis. That's undefined. But we wanted a gradient of 0, so that one does not work. So our final answer here is C. And you can see we can knock this over really quite fast. It feels impossible when you first see it, if you've never sort of encountered questions like this before. But once you know the tricks behind it, relatively straightforward. Of course, I'm not going to let you off the hook here. Here's a second question that looks similar to that one. Moving forward in time, this happened in Victoria in 2015. Give yourself 90 seconds, see if you can figure out what the answer is here. And I'm going to solve it in 3, 2, 1. Let's do it. I can use similar tricks here, right? But I've got small issues. In quadrant 1, I have both positive and negative gradients. So that's a bit of an issue. So I can't use that quadrant 1 trick. But look at quadrant 4, right? Every gradient there is negative. Okay, so we can deal with that. In here, we have both positive and negative gradients. But in here, we always have positive gradients. All right, so I can at least use this negative and positive idea for quadrant 2 and quadrant 4. So let's see. 1 over a negative x minus a positive y. So a negative minus a positive. So negative minus a positive. That's going to be negative, right? So I'm expecting this one to give me a negative gradient. But it doesn't. It gives me a positive gradient. So this one's out. Okay, what have we got here? A positive y minus a minus x. Well, that's going to lead to a positive. Positive minus a negative is a positive. So b is still in play. 1 over a positive minus a negative. 1 over a positive minus a negative. All right, so minus a negative is the same as plus. So 1 over y plus a number. So that can be positive as well. So we're good there. A negative minus a positive, that's going to lead to a negative, but we want a positive. So that's no good. And then finally, we have 1 over a positive plus a negative. Now, depending on how large the positive or the negative is, that would lead to a negative or a positive gradient. So that one's no good. So we're down to 2 options based on that thing here. Now, I can do the same thing for quadrant 4, but it's not going to break the tie here, right? Because these are essentially behaving in the same sorts of ways. So I can do the whole thing for quadrant 4, but it's not going to lead me anywhere. We really need to look for something special here, some interesting point. And the thing that we need to look for are either vertical lines or horizontal lines, because they tell us something, okay? So if we zoom in here, hopefully you can see some vertical lines. There's a vertical line there, a vertical line there, a vertical line there, a vertical line there, a vertical line there. There's a vertical line right there. All right, so let's focus on just like that vertical line there. So we know there's a vertical line at x equals 0 and y equals 0. A vertical line means an undefined gradient. So which of these would lead us there? Well, if we had 0 minus 0, we'd get a gradient of 0, which is a horizontal line, which is not what we're looking for at that point. So it's probably not B, which leaves me with C. So let's double check C. C, 1 over 0 minus 0, that's 1 divided by 0, which is undefined. C is our answer here. Now you might be asking yourself, what's with all these other vertical lines along here? There's vertical lines all the way through this kind of diagonal. Whenever y equals x, there's going to be a vertical line here because, let's say, y was equal to 5 and x was equal to 5, we'd have 1 over 5 minus 5, which is 1 over 0. That's why we're getting that line of undefined gradients when y equals x. All right, so lots of neat tricks here, but that's what you need to be thinking of. Not specific numbers, except when you're on like the x-axis and the y-axis, but thinking about the gradients and then looking for those y-axis points, those x-axis points, or any horizontal and vertical ones, and working from there. All right, now we're moving up to New South Wales, 2021, just last year. Give yourself 90 seconds. And I'm going to do it in 3, 2, 1, let's go. Okay, so this is super straightforward compared to the last question. We've got a vector equation of a line that's joining points 4, 2, 5, and b equals negative 2, 2, 1. Now the vector equation of a line is equal to a plus lambda d, where a is like a starting point and d is the direction that the line is moving in. So, which one of these has a as a starting point? All right, so we can choose 4, 2, 5 as a starting point, or negative 2, 2, 1 as a starting point. The only ones that have one of those as their starting point is this one and this one. So it's one of those two. So let's get rid of C and D. It's possible that it is C and D because maybe they're using some other third point that lies on the line as their starting point. But it's probably a good idea to be able to say, well, it's probably one of the points that they've started with. Could not be though. So let's check back in on that in a minute. All right, we want to find the direction that this line is traveling in. And the best way to do that, we've got a point A, we've got a point B that lie on this line. We're going to draw a line through them there. And so in other words, we want to know vector A, B, or maybe vector B, A, depending on which way they want to turn this direction around. But I'm going to assume it's vector AB. All right, we know that vector AB is equal to OB minus OA. A, and OB is equal to negative 221, and OA is equal to 425. Now we solve that and we get negative 2 minus 4 is negative 6, 2 minus 2 is 0, and 1 minus 5 is negative 4. Alright, so I was hoping that negative 6, 0, negative 4 would appear here, but it's not appearing there. And I thought maybe it's not AB, maybe it's BA. But BA is just, let's write that there. BA would be equal to the negative of that, right? So it would be 6, 0, 4. So I've still got a problem. But looking at the two solutions here, one of them is 3, 0, 2, which is half of 6, 0, 4. So if you imagine a particle moving along this line, lambda represents the speed that the particle would be moving along that line. So if we're trying to find a possible equation with this line, that speed could be anything. So as long as we've got a multiple of BA or AB in our equation of the line, then that's going to be it. So it's going to be B right here. Now you might be asking yourself, this feels messy, there's got to be a better way to do this. And there is a different way to do this, given that it is a multiple choice question. Now we can see that 425 sits on both of these. We narrowed it down to 2 before. Now if 425 sits on there, the only other question is, does negative 221 sit on there? Because if negative 221 sits on there, then we know that they both sit on there. So if we sub negative 221 into the vector equation, negative 221 equals 425 plus lambda 123. We can then try to solve that for lambda, right? So we can do negative 2 minus 4 is negative 6, 2 minus 2 is 0, and 1 minus 5 is negative 4. Lambda 1, 2, 3. Now there is no value for lambda that would make this true. So that means that negative 221 does not sit on that equation. However, if instead I was to sub it into that equation, negative 221, 425, and instead make it 302, we can see that there is a value for lambda. That value would be negative 2. So it must be this one there. So, two sort of ways to go about solving that question. Let's go on to the next one. All right, still tech-free, short response. We've gone to Victoria in 2007. 4 marks here, so you should give yourself about 6 minutes. Have a try. All right, and I'm going to solve it in 3, 2, 1. Let's go. So this is some weird relation thing. I have no idea what it looks like. For ease of thought, I'm going to draw something, right? I have no idea what this looks like, but I'm just going to draw like a circle because that's the simplest relation. It's not a circle. Let's make that clear, but I'm just going to draw that there. There's a point on there, 2, 3, and we're trying to find the equation of that thing. Now, I don't know if it has a negative gradient or a positive gradient, but this is just to get in my head what I'm doing, right? So if I know a point, the only other thing I need to know is the gradient. And in order to find the gradient of a function or a relation, we find the derivative of that. So that's what this question is really about, finding the derivative. So it's implicit differentiation we're doing here, right? So let's go in order from easiest to most difficult. The derivative of 2 is 0. The derivative of x cubed is 3x squared. The derivative of 2y squared is 4y dy dx. With implicit differentiation, if you're differentiating y, you need that dy dx on the end. And then finally we have this negative 2x squared y. And in order to do that one, I'm just going to break out over to here. Right, so I've got negative 2x squared y, and I'm going to have to use like a product rule to do that. So I'm going to let u equal negative 2x squared, which means that u dash equals negative 4x. I'm going to get v equal y, which means that v dash equals the derivative of y, which is 1, dy dx, which is just dy dx. Okay, so, and now I'm going to put all of this together over here. So uv dash is going to be negative 2x squared dy dx and VU dash is going to be negative 4xy. Okay, so now I just need to sort of group all those dy dx things together and get everything else over to the other side. So this 3x squared belongs over there as negative 3x squared. This negative 4xy belongs over there as positive 4xy. And I've got, I'm going to do this sort of a bit non-standard. Dy dx, actually it's not too bad. And then we've got negative 2x squared plus 4y, which means that dy dx equals negative 3x squared plus 4xy over negative 2x squared plus 4y. Now, I'm not going to bother trying to find some way to like factorize things or simplify things or do anything like that. I don't need to do that. I have a function for the derivative, which is good enough for me. Now, I want to know what the derivative is at that particular point, which means I need to sub in 0.23 into my derivative function. So, subbing 0.23 in, I've subbed in 2 for x and 3 for y, and don't get those confused. All right, and then let's just calculate that. And we get a nice little gradient there of 3. Neato. Okay, let's not forget what we were trying to do. It said find the equation of the tangent. So, a tangent, a straight line, y equals mx plus c. And we know that y equals 3. We know the gradient equals 3. We know that x equals 2. And we don't know that c value. So that c value is 3 minus 6, negative 3. Okay, we're finished now. Our final answer, therefore, y equals the gradient 3x minus 3. Okay, because I know you're curious, this is the function here, and we had a point right there of 2, 3, and when we find the equation of the tangent, you get something like this, y equals 3x minus 3. A little bit different to my sketch here, which was expected. We knew it wasn't a circle, we just drew a thing, and when I think of implicit differentiation, I tend to think of circular stylish shapes. Okay, last question. All right, this question comes to you from Western Australia in 2016. Have a crack at it, 7 marks, so about 10 minutes. And I'm going to solve it in 3, 2, 1. Let's go. So we have 2 points here, A and B, and there's some sort of sphere that passes through it. That's a sphere. That's my best drawing of a sphere. Okay, there's a diameter that passes through AB, and that's the key here, right? Because if that's the diameter, then there must be some part here that is the center of our sphere. Specifically, the midpoint between points A and B. And you should know how to find midpoints. Midpoint is half of the 2 vectors added to each other. Okay, so doing all of that, we get 2, negative 1, 4 as the center. So this point right here is 2, negative 1, 4. All right, so if we want the Cartesian equation for the sphere, we need 2 things. We need the center and we need the radius. Now, there's 2 ways that you could go about finding the radius here. You could find the distance between point A and B and halve it, because that's the diameter, half of that's the radius. Or you could come a little more directly at it and find the distance between A and this new point, because that is the radius. Given these are all written here, I might just do that and then divide it by 2. I've got to say I immediately regret this decision because I'm going to come to a surd here and then I've got to divide the surd by 2. Whereas if I just found the distance between the midpoint and A, I would have a surd still at the end, but I wouldn't have to divide it by 2. So I feel like I've made some extra work for myself here, but whatever, right? So this is 4 times 6, which is 2 root 6. So that's the diameter, right? Which means that therefore the radius equals 2 root 6 over 2, which is root 6. Okay, again, this is not the right way to do it. I really think I should have just gone from here to here. But I want to show you what happens when you sort of go down a wrong path and you either have to keep traveling down that path because you get to the same answer with a bit of extra work, or you should have just made the right choice in the first place. So finishing this question off now, I've got everything that I need for a equation of a sphere. I have a center and I have a radius. So therefore the equation of the sphere is x minus 2 squared plus y minus minus 1, so y plus 1 squared plus z minus 4 squared equals 6. 6 because square root 6 squared is 6. Don't forget to square that on the end. A lot of people write root 6 here. That's wrong. All right, there's a little bit going on there, but nothing we can't handle. You see I sort of took a wrong turn, but I think it works out okay. Let's look at part B. And we're not really using any of the stuff from part A for part B, except for what was in the question, which is those points. Okay, if point O is the origin, consider the plane that contains vectors OA and OB. All right, so that means that we know that, if you like, point A is on the plane, point B is on the plane, but so is the origin. And that's going to become important for something at the end here. Okay, so if we want to find that, we need to find a vector that is normal to both OA and OB. We need to find this normal vector that makes right angles with both of those. To do that, we're going to use the cross product. Now, if you get turned around when you do the cross product, it's a good idea to grab your formula sheet and just do exactly what it tells you to do, right? So here it says this times this is going to be equal to A2 times B3 minus A3 times B2. And if you follow those directions, you can't really go wrong. All right, so I've done it. I've got 6, negative 20, negative 8. That is my vector that is normal to the plane. Now again, if you want to use a different version of the cross product, I know I've taught little matrices that allow you to do the cross product, but if you've gotten to this stage and you're preparing for your exam, use your formula sheet. Okay, from here, we want to find the vector equation of a plane. Okay, so I have this equation here, and that's the equation we're going to use. So R is just an arbitrary thing on our equation. And we have 6, negative 20, negative 8 equals A. Now, what's A? A is any point on the equation of our plane here. So you can choose literally any point on the equation of the plane and we're going to end up in the right spot. Now, what should I use? Well, I know one of the points on my vector, on my plane, is 0, 0, 0. The origin is in the plane, right? And if I use 0, 0, 0, dot product of my normal, 6, negative 20, negative 8, I can save myself some hassle here because I know the dot product of 0, 0, 0, dot 6, negative 20, negative 8 is going to be 0. Alright, and I am done. Now, it would have worked if you put in a different point. For instance, you knew point A from here, and you knew point B from here. And you can test that for your own curiosity, but knowing that the origin on the plane is going to save me some work here. Alright, that's the end of that question, part A, part B. Those are the 4 questions today. Alright, so looking at what we've done here, we've done 2 tech-free multiple choices. We've done 2 tech-free short responses. Looks like we've got a little road ahead of us. At time of recording, I think we've still got about 25 days left before our exam. Still plenty of time to get through this stuff. Still plenty of time to revise yourself. So, little bits. Don't try to figure out the whole exam today. Just little bits, day at a time. Topic, topic, topic. Good luck. I'll see you in the next one.